Hi friends, we're going to do 1.6 today. Can you identify curves, regions, and identify polygons and circles? Whole bunch of things in this section. And I'm just prepping you because there's a lot of definitions. So get your highlighter ready. The first thing we're going to talk about are two-dimensional figures or planar figures. This should be kind of like a thing right here. And these are figures that lie entirely in a plane. Okay, these are figures that lie entirely in a plane. Last chapter, we kind of started with the ruler postulate, and I thought it was important that we re-go over that again. The ruler postulate, once again, states that every point on a line divides that line into three sets, the point and the two halves of the line. Okay, well, why do I want to kind of introduce you to this again? Well, it's because of these definitions that are coming up. We're going to look at curves. So a curve is different than a line segment. Okay? We have different classifications of curves. So first, let's define a curve. A curve is a continuous set of points. This is something you can create without lifting your pencil. Okay? If you look at figures A, B, C, and D, all of these figures A, B, C, and D are examples of curves. Now there's some classifications of curves. The first one we're going to talk about is a closed curve. A closed curve, you end at the same point where you began. For example, C and D. If I start at this point, trace around, I will also end at that point. D, if I start at this point, I'm going to trace around and end at the same point I began at. Now, simple curves are a curve in which you will never recross your path. And we're going to do, if you did the enrichment exercise, I believe, from 1.5, you worked on this with polygonal figures instead of curved figures. But you're never going to cross your path again. So A and C. So on A, if I draw it, obviously I don't redraw. C, obviously I don't redraw. Non-simple curves are like B and D. Okay? They are not simple curves. It means we kind of cross over a little bit. See how I cross over my path when I trace B. All right. A circle is a set of all points in a plane, a given distance from a given point, the circle's center or origin. That distance is the radius of the circle. When we name a circle like this. We look at the radius is point C. So this is circle C, really large, but circle C. And that's how we name a circle. So let's look at example 1. Let's take what we kind of learned and apply it to example 1. Can a circle be classified as a curve? Can it be a curve? Well, yes, it can be a curve. Because the definition of a curve is it's a continuous set of points. We can make a circle, we can trace a circle without lifting our pencil. So yes, it is a curve. Is it a simple curve where we never cross our own path? Yes. Hopefully, once again, when you draw your circle, you start at one place, go around, and finish. Is it a closed curve? Is it closed? So what we mean by closed is it like A is not closed and B is not closed. So if we're looking up our example, closed curves, there's no open ends, right? Remember when we said that with closed curves? So yes, a circle is a closed curve. Okay? The interior of a circle is the set of all points whose distance from the center is less than the radius. What do I mean by that? Well, here's the center of my circle. Just pretend that's directly in the center. The interior is this gray space. It's every point that is less than the radius. Now, I don't say less than or equal to the radius, because if it was equal to the radius, it would be lying on the perimeter of the circle, right? The exterior is the set of all planar points whose distance from the center is greater than the radius. So this is this space out here, the exterior of the circle. Sounds pretty basic, but we need to understand that clarification. The internal is inside in here. This is that red or the gray area. External is the green. All right, like I said, we have lots of definitions this section. So here are a couple more. The region. The region is the union of a simple closed curve and its interior. The curve, the actual black line in this example right here, the curve itself, the black line right there, that's a horrible arrow, but you know, if we keep doing it, it'll get better. The black line is called that region's boundary. Okay, we've all played enough sports where we understand that the line around the field is the boundary. So think of it like that. Next definition are concave and convex. Any set of points can be either concave or convex. Concave, I think of it like this. It caves in. So when we look at this polygon right here, see how it kind of caves in on itself? This is concave. Convex is where it does not cave in. Now, the one thing I want you to look at is the red diagonals, because this is your kind of technical definition for concave and convex. Okay. If you can draw at least one segment, between 2 points that is on the outside of the figure, like that line, it's on the outside of the figure, we're 2 points, and now that line's outside, it's concave. If you can take that red line and connect 2 points of the shape and it always lies inside, it is convex. Okay, that's the technical part of the definition that you're going to need to remember. All right, last couple definitions right here. A polygon is a simple closed curve that consists only of segments. So a polygon is a closed curve. Even though I say curve, it's not fluid, but remember, the definition of a curve is a continuous set of points that I can trace without lifting my pencil. So I can create this pentagon, and I did not lift my pencil. So even if it doesn't curve like a circle or an oval like you're expecting, a polygon is still a closed curve. Each segment is called a side. So each segment is a side, and each endpoint is a vertex. Okay, so in this pentagon over here, I've got 5 vertices and 5 sides. All right, so let's look at example 2. Determine whether each figure is a polygon. Is A a polygon? Yes, A is a polygon. It is a simple closed curve, and it consists of segments. What about B? Is B a polygon? No, B is not a polygon. The reason B is not a polygon is because it has one side that is not a segment. It's not a segment. So therefore, it's not a polygon. C, is C a polygon? Yes, it's a concave polygon, but it is a closed curve consisting of line segments. D, is D a polygon? No. First of all, it's not closed, but it is comprised of segments. But If it's not closed, it cannot be defined as a polygon. All right.
She said maybe.
Couple more definitions for you here. Equilateral polygon. An equilateral polygon is a polygon in which all the sides have the same length. An equiangular polygon is a polygon which have all their angle measurements are the same degree. A regular polygon is both equilateral and equiangular. We have a lot of theorems that help us with regular polygons that we will learn later on in the year. But just remember, regular polygon, this is not going to be pretty because my drawing skills are So we're going to pretend. I'm going to put markings on this. All of these sides are exactly the same length, making it equilateral, and all of these angles are exactly the same length, making it equiangular. Therefore, this is a regular pentagon. Over here, we have our all of our fun names for polygons. We all know triangles and quadrilaterals, pentagons, and you guys have had enough Latin now where you can go up through hepta and octa and decagons. It gets a little confusing when you get to 11 and 12. Hendecagon is your 11-sided figure and dodecagon is your 12-sided figure. To be honest, anything above 12 sides, I don't know the name for. I can look it up real quickly, but I'm not going to sit around and kind of memorize all these names. If you ever have a question or if you have a problem and it's asking you to find the number of sides or the area of a dodecagon and you can't remember, ask the question, okay? Ask the question. More definitions. Polygons are named by listing the vertices in consecutive order. You can either go clockwise or counterclockwise. Okay, so if we look at this pentagon over here on the side, that is pentagon A, B, C, D, E. Or it can be pentagon A, E, D, C, B. We just pick a point and go around. A vertex is where two sides meet. So all your lettered points, A, B, C, D, and E, are vertices. A diagonal is any segment that connects two non-consecutive vertices. Okay? Okay, I don't know why I put vertices on our opposite sides. I don't know why those words were typed. So just mark those out. Next definition is perimeter. Perimeter, as you know, is the distance around a closed curve. To find the perimeter, you just add all the sides together. So example number 3. Classify each polygon by the number of sides, then state whether it forms a concave or convex region, and whether it is equilateral, equiangular, or none of these. So first of all, let's look at how many sides. Let's count 1, 2, 3, 4, 5, 6, 7 sides. So if it's 7 sides, it's a heptagon. Okay, so it's a heptagon. Is it concave or convex? So I'm going to use my diagonals, and I'm going to look at my diagonals, and I'm going to take my red pen. If I connected these two vertices, that diagonal lies outside, so it is concave. Okay, concave. And if I'm looking at the markings on the picture, and I'm going to erase this real quick. If I'm looking at the markings on the picture right here, all the sides have the same one little tick mark. So it is equilateral. Equilateral. Okay, so let's look at figure number, or letter B. Figure letter B. Figure letter B. That works. All right, there's 4 sides, so it's going to be a quadrilateral. Quadrilateral. It is convex. I can't, any diagonal I draw would be inside my figure. So it's convex. Convex. And is it equilateral? Let me look at all the sides. I've got a 3 tick mark, 2 tick mark, a 1. Nope, it's not equilateral. Is it equiangular? No. I've got 4 rainbows, 3 rainbows, 2 rainbows, and 1 rainbow. So none. Neither. Look at C. First of all, let's count the sides. 1, 2, 3, 4, 5, 6, 7, 8. 8. Octo. O-C-T-O, gone. Octagon. Convex or concave, my diagonals would all be inside, so it's convex. And is it equiangular? Yes, all angles are the same. Is it equilateral? Yes, all sides are the same, so it is regular. All right, so let's go on to our next theorem and look at our theorem. This theorem, like a lot of theorems, does not have a name, so don't always get accustomed to theorems being named like Ruler Postulate or side angle side theorem. This one just does not have a name. So sometimes you just have to say the theorem that says blah, blah, blah. So this theorem says that the perimeter of a regular n-gon, n meaning the number of sides, so it's just n number of sides, with sides length s can be found using the formula perimeter is equal to n times s, the number of sides times the side length. So let's look at example number 4 and what we mean by that. I'm going to start off with doing B first, because B is a regular n-gon. All the sides, at least, let me say this. It is equilateral, at least. But without going into it, it is a regular pentagon. So we're going to use the formula P equals NS. So the perimeter is equal to the number of sides. There's 5 sides times the length of each side, which is 9. So the perimeter is 45 units, whatever the unit is, 45 units. In A, our problem is just a little bit more complicated because they are all different. But hopefully we all remember to find the perimeter, we just add up all the sides. So 4 plus 8 plus 10, oh, that's 12 plus 10. 12 plus 10 is 22 units. So our perimeter is 22. Oh, this one actually gives us a unit, centimeters. Oops, centimeters. Last 3 definitions of this section. A chord. And we're going to get more into chords and arcs later on in the year, but a chord is any, not only, any segment whose endpoints are on the circle. A diameter is a chord that goes through the center of the circle. And an arc is in red over here in our picture, a curve that is a subset of a circle. All right. Our last theorem of the day is the circumference C of a circle with diameter d or radius r can be found using the formula C equals pi d or C equals 2 pi r. This is something you have been given these formulas before, and you know that the circumference is pi times the diameter, because pi is equal to circumference divided by diameter. So pi is equal to circumference divided by diameter. And I'm going to read you guys a fun book when it comes to Pi Day that helps us explore this. So look at A, find each missing measure. The circumference is 10 centimeters. It wants us to find the radius. So we're going to use circumference is equal to 2 pi r. Well, the circumference is 10, 2 pi r. Use some algebra, divide both sides by 2 pi, and we get, oh, there we go. 5 over pi is equal to r. You could put it into a decimal. If we put it into a decimal and we type into our calculator 5 divided by pi, it would be 1.59 centimeters is our radius. Okay. B, find the circumference of a water tower that measures 60 feet across. So here's our water tower. That line up there is 60 feet. Okay, so we want to find the circumference. Now, if it's 60 feet across, that's the diameter. So we'll use pi d for our formula. So circumference is equal to pi times the diameter. The diameter is 60. So the circumference of this water tower is 60 pi. Now, if you needed to find it in numbers and you didn't want to, like you were going into the hardware store and you needed to find a piece of rope that would go around the circumference, you can't go into the hardware guy and say, I need a piece of rope that's 60 pi long. You would need to multiply 60 times pi, and that would give you 188.5 feet rounded. Okay? But if you left your answer as 60 pi, I would gladly accept that. All right, so problems we're going to work on tomorrow are 1 through 29 odd. Again, remember to fill out your TRF tonight and come to class with problems for us to look at.